Hi everybody. In the previous video we talked about the hydrogels and how they have to be designed in order to provide a good condition for the cell's growth. We talked about the growth factors, their RGD, the vascularization, but we didn't mention anything about the mechanical properties of the gels. Well, in this video, I want to provide you an overview about all the things that we are going to cover within the next slides of this topic about the injectable nanomaterials. And after it's finished, we will go through the slides with more details. So, consider this picture. You see here that if we have a solid material and we apply a force in tangent to its surface, the amount of force divided by the area gives us the stress. So this is the amount of stress that we apply on this solid. And based on the amount of stress that we apply, we will have a deformation. This deformation is called strain. So what is the relation between the amount of stress that we apply and the amount of strain that is obtained? Well, you see here that as we increase the amount of stress that is applied on our material, solid material, the deformation is increasing more and more. So the relation between these two amounts, the stress and the strain, is defined by this modulus of G. So for the rest of the slides, you will see that we will calculate the modulus both for solids and for liquids and also for the hydrogels. And by comparing these G modulus, we will realize whether we have a solid, a liquid, or a gel. Okay, let's have a look at this picture. You see here that for a solid, when a stress is applied and a deformation strain is obtained, the relation between them, let's name it G prime. So this is the modulus. On the other hand, for the liquids, you see that you know that the liquid is a material which cannot resist over the shear stress, so it will deform easily. So based on the viscosity of the liquid, we will also define another modulus which is called the G double prime, and we will see that for the hydrogels we will have a modulus which is a combination of both the solid and the liquid, which is something in between. And you will see that this is a real number and this is an imaginary number. So for the liquids, we will reach into a G double prime as an imaginary number, and for the solids, G prime as the real number. So for the hydrogels, the properties of both materials will be present. But the question is that how are we going to calculate the amount of G prime and G double prime? Well, it is done by the help of a machine which is called the Rheometer. Well, it consists of two plates, the bottom plate which is fixed and the upper plate which can oscillate, which can rotate, and in between we have our material. Well, it applies a sinusoidal stress on our material, and we can measure the amount of G prime and G double prime. And remember that G prime is the modulus corresponding to the solid phase, and G double prime is the modulus corresponding to the liquid phase. And you will see that we will have this diagram which tells us, if you consider a material that is under the rheometer and the amount of G prime and G double prime is being measured continuously over time, and a reaction is happening in this material, a reaction which is cross-linking all the polymers of this material together. You will see that as the time goes by, their cross-linking is happening more and more. At the beginning, the G double prime for the liquid is greater than the G prime for the solid. So we have the colloid, we have, let's say, the liquid phase. But at this point, the modulus of the liquid and the solid will be the same. And by the passage of time, the modulus of the G prime corresponding to the solid phase will overtake over the G double prime of the liquid phase. So this is the point that we can say our material is becoming a gel. This is the gel point. So this is all you have to briefly know about the mechanical properties of the hydrogels, and we will continue with the slides of the course.